For our next set of examples of series in section 11.2, I want to focus on a very specific series called a geometric series. Now, we already looked at geometric sequences in the sequence section, so now we're going to look at adding up those terms. So a geometric series is any series that can be represented in this form: the summation from 0 to infinity on the index of a times r to the k. So it's going to look like a plus a times r plus a times r squared plus a times r cubed, and so on and so forth, where a is the first term and r is the common ratio. So just one note here I want to add in. I want to go ahead and add in one other way in which we could express this, because sometimes we do express this with the index starting at 1 rather than at 0. So this could be expressed as the sum from k equals 1 to infinity of a times r to the k minus 1. Now we're using k here. We can use any index, any variable we want on the index, but we're using k here. So just as a note, for these sequences, a represents the first term, for this series, the sum of the sequence of terms, a represents the first term, and r represents the common ratio. So how much are we going up? What is the factor we're going up by for each of the terms that we're adding up here? So again, if we're going to look at a series, what our interest is to determine if this series, this infinite sum, has a finite value. So does the sum have a finite value, or is it infinite, or maybe it does something in between, like it oscillates but it doesn't approach a finite value, something like that. And so again, we talked about this in the very first video, but it is not an easy task to express the partial sum for most series. But for this series, we actually can. And so if we consider what and I'll just walk through this proof right here below. If we consider what the partial sum is, it's the sum of the first n terms. Since we're starting at 0, the first term would be just the constant a plus a times r plus a times r squared plus a times r to the n minus 1. That adds up, because we're starting at 0, that does actually add up the first n terms. And if we express that down below here, and then right underneath it, if we just multiply that by r, so we multiply by that common ratio, what we get is essentially a shifted sum. So then the sum becomes a times r plus a times r squared plus so on and so forth, and we have the a times r to the n term. So I just stack these on top of each other in this proof here. And if I were to subtract, so if I were to come in here and say, well, let's just subtract those two lines. If I subtract those two lines, notice what happens. All of the terms except for a and a times r to the nth have canceled out, and I have the difference of the two, s sub n minus r times s sub n is actually equal to a minus a times r to the nth power. Do a little bit of factoring, and notice I can actually solve for the partial sum. And so the partial sum of a geometric series is a times 1 minus r to the nth over 1 minus r. And then we can just break this down and take the limit of this for each of the different possibilities for that common ratio. So if the common ratio equals 1, if I just plug 1 into this right here, what I end up getting is that this partial sum approaches infinity. And the second case, if r equals negative 1, I get oscillation. So for both of those cases, that is actually going to give me divergence. And I will leave that for you to plug those in. It's pretty easy to plug in those r's and then see what happens. So then I would get divergence. So if I plug in 1 or negative 1, and you would actually need to do that for the 1 all the way back to the original, and you'll just see you just be adding up a bunch of terms, and that's going to approach infinity or negative infinity or oscillate. Now, if you plug in r in absolute value less than 1, and we actually take this limit, you can see that the limit of that one piece right there, r to the n, that's going to approach 0, and so this actually just approaches a over 1 minus r. And if we plug in something bigger than 1 for the common ratio, so if our common ratio in the geometric series is greater than 1, well then the limit as n approaches infinity of s of n isn't going to exist. We're just going to have something that does not exist there. And so what we get is we get infinity or negative infinity or oscillation. Something occurs that does not exist. So that summarizes it for the does not exist. And we get this really nice little summary of what happens to geometric series. So for a geometric series, if we have a geometric series that can be expressed in this form, now again, we could reindex that if we wanted to, but if we had a geometric series that can be expressed in that form, we know that it will converge. Not only do we know that it will converge, but we actually know what it converges to. It converges to A over 1 minus R if that common ratio is less than 1. And if it's that common ratio in absolute value is greater than or equal to 1, well, then this geometric series will diverge. Okay, so that's our summary, and that was a fairly quick run through of that proof. But that's how we can do it for these geometric series. We can look at them and we can basically know right away if we can identify what that common ratio is, we can know if it converges or diverges. And if we know what the first term and the common ratio is, we would know not only that it converges, but what it converges to. So I want to run through a few examples here for this type of a series. So I have several examples, and we can run through some of them in the video and some of them in the class sessions, but let's take a look at this first example. So for this first example, if I were to have 1/2 plus 1/4 plus 1/8 plus 1/16 plus, this is obviously a series, an infinite sum, and it is geometric. And so what we would probably want to do first is just express it as its geometric series. So let's do that for some practice and then talk about whether it converges or diverges. So I forgot for just a second if it started at, it starts at 1/2. So if it starts at 1/2, so we've got 1/2 plus 1/4 plus 1/8 plus 1/16. And we want to express that, and that goes on and on, but we want to express that actually as a series. So we want to introduce the summation, and we want to say, well, what is this going to be? Well, there's a few ways to do that. We could, if we wanted to, we could say that this is from, and it doesn't matter what index you use, I'll go ahead and use k. So if k equals 1 to infinity, if we start the index at 1, well, the first term is 1/2. And then the common ratio here, so my first term, let's do that in red. My first term right here is 1/2. And then notice that to move up from term to term, we're multiplying by a common ratio of 1/2. So each time we're multiplying by a common ratio of 1/2, sometimes we can see that visually. Depends on how you recognize that pattern, but you can see that you're bumping up. So then this next term is a times r, and then a times r squared, and then a times r cubed, and so forth. And so since we started at 1/2 as our first term, we've identified that a equals 1/2 and that r equals 1/2. Now there are other ways to come up with r. R is the common ratio, so you can also look for r by looking at the ratio of the terms. So you take the k plus 1 term and divide by the kth term, and that would give you r. So you could take 1/4 and divide by 1/2, and that would give you 1/2. And it doesn't actually matter which of the two adjacent terms that you look at. I grabbed the first two, but you could have grabbed 1/8. So notice that this would be the same if we had taken 1/8 and divided by 1/4. We would also have gotten 1/2, and on and on. And so as long as that common ratio between two adjacent terms throughout the series is the same, then that becomes our r. So there's a couple of ways that you can identify. You can look for the patterns, you can look at the ratio of the terms, look for the first term in the series, and then just look for the ratio of the terms, or look for the patterns as you're writing out the series. But either way, we've got a times, and then we end up with that common ratio, 1/2 to the k minus 1. All right. Just as a note, I'll just put it in a different color, I guess, here. Just as a note, again, kind of with the re-indexing, there's lots of ways to express these series or back-end sequences, lots of ways to express sequences. If we'd wanted to start this at 0, for instance, so if I just wanted to start at 0, let's use a different, well, no, I'll just leave k. If we started at 0 and we wanted to express this starting at 0, we absolutely could have. We could have written this as 1/2 times 1/2 to the k. starting the index at 0. That will generate the exact same series, just a slightly different start on the index. Okay? And of course that adjusted the power on the common ratio as well. Okay, so all of that was said just for what if we're given the series and we have to identify what A and R and write it in actual geometric series form. But once we've got it in this geometric series form, if we know what A and R are, then we know that it converges or diverges, and if it converges, we know what it converges to. So we identified that there and talked about the different ways that we could identify that first term and that common ratio. But since that common ratio is equal to 1/2, which is clearly an absolute value less than 1, this tells me that the series converges, and we know that it actually converges to. We know exactly what that sum. It's super powerful actually here, because not only do we know that it converges, meaning it has a finite sum, but we know what it converges to. We know what the infinite sum of these numbers actually converges to. So we know that this series, 1/2 times 1/2 to the k minus 1, we know that it has to be equal to its first term over 1 minus its common ratio. So we're using that formula that this is coming from the formula A over 1 minus R. And we know that, of course, that's going to be 1/2 over 1/2, so that actually is 1. So not only does it converge, but we know that it converges to 1. So this geometric series converges to 1. So I have lots of information here talking about how to write the series as a geometric series, and also how to identify A and R, the first term and the common ratio. But once we've done that, however you do that, whether you do that through patterns or looking at ratios, you are going to come up with a way to determine if this geometric series converges or diverges. All right. So let's look at, again, I've got several examples here, and I want to jump actually to this one next. So I want to jump down here to this number 4. And so number 4 here, what if we had the series from k equals 6 to infinity of pi to the k? So let's take a look at that over here. So I'm going to carry that over here so I have some more space. And this is the 4th example in my lecture notes. And so we're going to go ahead and start with this one, and there are, like I said, I do have more examples, and if you guys want to see some more, we'll do those in the class sessions. So if we started this, and now this is geometric, it's shifted index, so the index has been shifted off to 6. So if I were to actually write this out, this would actually be pi to the 6th plus pi to the 7th plus pi to the 8th plus pi to the 9th, on and on and on we go. And you probably can get a pretty good sense right away that this is not going to converge. We are adding ever increasing numbers, and they're positive, so this sum is definitely going to be approaching infinity. But how do we show that? How do we play with that with a geometric series? And so what I want to talk about is just a little bit of summation notation on this. And it turns out that this particular series, if we're saying that we want to start at 6 to infinity, well, if we want to use the proof that we did earlier with geometric series and be able to say that this does diverge because its ratio is too big, then we do have to do just a little bit of work here and show a little bit of notation. And so what I would say here is that, well, this is exactly the same as saying that this is the series from k equals 0 to infinity of pi to the k. But then we subtract off some finite terms to get that to start at 6. So this is the series from k equals 0 to infinity, and then subtracting off a couple of terms here. So then we would subtract off the terms from k equals 0 to actually k just equals 5 of pi to the k. So think about what we're saying right there. We're just saying, and this is true of summations. This is just some summation definitions. This is saying this right here is just a finite number of terms. This is saying, well, what if we add it up? So pi to the 0. So this would be 1 plus pi squared plus pi cubed plus pi to the 4th plus pi to the 5th. This is subtracting off. So we're saying subtract that off of this infinite sum. Oops. subtract that off of this infinite sum, and this over here is the sum starting from 1 and going all the way to infinity of those pi's to the power. So we're subtracting that off of this infinite sum here, and that would give us what we were starting with. Well, now we can look at that theory because our theory was working from an index of 0. And so now we can say, well, think about that. What happens to this geometric series? This geometric series has a first term of 1 and a common ratio of pi. Okay? And so again, the first term, and I'm just looking at that, you can look at that as 1 times pi to the k, or you could even just plug in the first index, k equals 0, of course that's 1. So the first term is 1, and the common ratio is pi. Well, pi is in absolute value, and its magnitude is the same, is greater than 1, which means that this must diverge. This diverges, and it diverges actually in a very specific way. It diverges to infinity. And if this diverges to infinity, and then, I mean, who cares what this specific value is? We could plug it into a calculator and add those all up, but we know that that's just some finite value. So we're taking away a couple of terms from infinity. So then we're taking infinity and we're subtracting a couple of terms, a couple of numbers here. Well, that is going to continue to be infinite. So this is infinity, and we would say that this series diverges. So turns out with series, if you've got a couple of, and when I say a couple, I mean a couple could even be a million terms. If you have a couple of terms that need to be added or subtracted to an infinite sum or to a finite sum, it's not going to change the convergence or divergence. So that's an idea that we will revisit as we work with these, but it's a nice one to do right here since we're talking geometric series. And if you've got a shifted index like this, well, then you've got a finite couple of terms that in this case, we're taking away. We're taking away a couple of finite terms from the infinite geometric series in its standard form from 0 to infinity. Okay, let's do, I think we're actually going to stop this first geometric series video here, and I'll publish this one, and then we can do a couple more in the second video or in the class session.